Hello, today we will create an ELF binary by hand. My goal with this video was to demystify the ELF format a bit. It's just a file format. It's a very complex one because it has to support many use cases and multiple machines, different CPU architectures. But yeah, it's just a file format. When I encounter a complex thing, my type of learning is to look at it from multiple angles. And the angle today will be writing an executable binary. We will accidentally create the smallest 64-bit binary that is possible in ELF, but that was not the goal. The goal was to cut out all the things that are not needed for a working Hello World application. We will write every byte in this ourselves, but we will steal from many sources. You will see what I mean under this. So what is the main source of information? It's the fifth man page of for ELF. The fifth page on main pages are about file formats, and this is a pretty good description. You can also find this online if you search for this in Google or other search engines for Man5 ELF. You will probably reach Michael Carrick's website, which describes the same thing. But on your machine, it's just you can go there directly. So this is complex, and I will focus only on our goal or our end goal. We will grab only the information that is needed for an executable. So what's the main thing to know about ELF? The very first thing is that every ELF file has a header. The header can be at a different length. So this is the header in C. The N is actually can be 32 or 64 bits as well. Yes, it describes these two. Well, if you are coming from a C background or C++, then there is nothing interesting for you here. So these are just we have a couple of type defs, and then it uses those ones. I think the interesting thing is that it starts with a 16-byte long array, and which starts with the 4 message, these 4 magic bytes. Like okay, this is just a byte, but then the word ELF in it. That's every file format has some magic number in it. This is ELF's magic. We could start writing our ELF binary by just looking at this and going over all the fields in it and pick one that makes sense. For example, my CPU is an AMD 64 CPU. So for the class, I would choose this one because it's a 64-bit architecture. Then the CPU has a 2's complement little endian machine. This one is not that clear, but it has to be, whenever we see these, it has to be the current one. And the ABI, now this is also not that clear. So this is why we should look at a few examples, a few binaries on our system and steal from them. What do they use? We will actually use the system v ABI. Think of this as the baseline that many Unix systems support, and we will not need anything else. But you can see here that there is also a Linux ABI, but that's we won't need that, even though this will be a Linux this is a Linux system. Okay, before I just wanted to give you a quick glimpse of the header. We will get back to this when we start writing code. So where was I? Every ELF binary needs a header, and then basically nothing else is needed. Well, it depends. An executable will need a program header after this, But if it's not an executable, then the program, you don't have to have a program header. So that's what I mean. Everything else is optional based on what is your use case. I foreshadow what we will need for the simplest executable. We will need a header, then we will need a single program header, which will tell us which will tell the program loader of Linux where to map our code. Our code will be in this file, of course, as well, not just these structures. And the program header will tell the program loader that at which offset is our code and where to map it in the virtual memory of the process that that it is creating. And that's all. We don't need anything else. Okay, before we start writing this code, let's play with existing binaries a bit and take a look at what is in their header. Let's write first just the hello world in C. So this is just a print hello. So the first thing we can notice is that it's 17K long. It seems like a lot for a hello world. But what we are in, let's check whether this is working. Yes, it works. Okay, we want to look at the header. The basic tool we can use to examine different sections of an ELF binary is the readelf command. It would be really nice to implement readelf. We could easily do that. Maybe that I will do that in a different video. The -h means not help, but the header. Show me just the header. So as you saw before, this is the 16-byte long array this is the first line in the struct. And actually these are coming from these. So yeah, this is ELF, but the rest of these are coming from this array. It just shows it in this format first and then that format first. What is the first thing that is not coming from there? Maybe this line. Never mind. But this surely comes from there. Okay, let's go through it quickly. So this is a 64-bit ELF binary that we got by default. Two's complement little endian because this is what my CPU is, version 1 current. That this is where we could steal that setting, and it's a system v ABI. So Linux supports multiple ABIs, and this hello world did not need anything else. ABI version 0 type. Now this is the first surprise. This is an executable, but here it says that this is a shared object file. Why? Oh, we will get back to this. Okay, AMD x86-64. And we have an entry point address. This is important. The entry point will tell the process that the program loader creates when it starts parsing the ELF binary, that this will be the first instruction in the virtual memory where the program can find the first instruction. So this is where it will start. And start of program headers, the ELF header is 64 bytes long. So the program header will start right after the ELF header. And it also has some section headers, and this is where they start. So we probably have plenty of program headers to push those out a lot. Size of this header is 64 bytes. Size of program headers is 56, so they have plenty of stuff as well in them. And we have 13 program headers and 31 section headers. I will not talk about section headers today because we don't need them for a working binary. But you can see immediately that even just a hello world compiled from C has a bunch of things in it, and it's really hard to understand ELF just by looking at this binary. We can take a quick look for the program headers. It's -L, don't ask me why. So these are the programs. These are the 13 program headers, and each of these lines basically tell that what to do, or they can have different types. But when we see load, then this means that it has a file offset. It says of which file offset and to map to which virtual address. So these are pieces from the file on this size, and these are pointers in the virtual memory that in the process that we are creating, and what to do with that. And so basically it takes those sections from the files and maps them to the virtual memory, sets their permission. In this case, this will be a readable page. And yeah, so it grabs all of these load types. So this one starts in this offset in the file. This will be executable. This means that this is where the code is located, where the object code, where the actual instructions are. This could be some data. Same here. This is readable, writable. So this could be also some kind of data fields. And we see a bunch of other stuff. Now, we don't want to understand this, but just one last thing. There is an interpreter here. And you remember that this is not an executable, but it is a shared library, which is surprising. And it has an interpreter, and the interpreter is actually the dynamic linker. That's what interprets it. Okay, what's going on? So the reason, so let's go back here. So its type is a shared object file and not an executable. Let me show again the ELF page. So what we would expect here, not the ABI, but the type. So there is the unknown type, relocatable file. If you are coming from a C background, relocatable files are when you are creating these object files in the middle of assembling a big program. So you compile a translation unit, and it gets these .o files, and those types will be this. Executable are the executables. And these are the shared object files. And there are also core files, which are like core dumps when the program crashed. So this is a dynamic library. So what is happening here is that Linux reuses some features from the dynamic loader, dynamic linker, and shared object files for security. So it by default, the system compiles every binary with position independent code. And why? Because at runtime, when it loads it up, it wants to randomize the memory addresses, and we can check that. We can let's rewrite our code to not die that quickly. So what we are doing is that we will just, in a loop, we will sleep 1 second. And the reason is we want to look at the mappings of the process. So let's start in the background. So we got the speed, and then we want to look at 952. The maps in the proc file system. And what are we expecting? So these are the executable pages. We have actually plenty because we have the dynamic linker and the libc, and this is our code. And this is where it maps in the virtual memory. Let's remember this last part, 2f and 30, or f2f and a lot of some 0. This is where it mapped now. Let's kill it and run it again. So again, proc 952 4 and maps. Now it run again, and yes, it changed. So this is what's happening. So this is not an executable. It is actually needs an interpreter, the dynamic linker, and that's the one that interprets it and runs the code actually. So this is immediately there is this barrier in understanding when you are just looking at the hello world. There is a lot of history here. We can change something and force it to look differently. Let's recompile it as a static binary. And let's look at it now. Now its type is an executable because we asked it to be static, not a dynamic. We overwritten this default thing, and this is our entry point. Let's run it again and let's take a look at the mappings in it. And one other thing is that this was system V before, and now the ABI changed to Unix GNU. Oh my god. Yes. Okay, let's run it again. (968). I think we left running the previous one. Let's kill both of them. So what was it? This was that one. This is the executable. Yes. So you see, it did not remap it because it can't remap it anymore. This dynamic remapping, this protection, this security protection doesn't work for static executables. It needs a position independent code. So that will reuse the shared libraries and the dynamic linkers. Okay, now that's out of the way. We will create an executable and a static with our virtual addresses in the object code. When there will be one moment when we need an address that will be a global address. Our code will not be position independent. Okay, let's kill these processes. I think we are ready to create, at least write our header and see what happens. So we will create a header, write it into a file, and we will look at it with the readelf, and then we will move on to the next section. Oh, by the way, this file elf.h, I did not talk about that. Where is it? So it's located here. This is what we will use. So this is what we see in the man page. It has the definition of these structures that we will just pull. That's why we write C code, because this is immediately usable. But this is independent of the programming language. We could write this in Python as well if there is a helper for this. We just write bytes to a file. That's all. But this is so handy that we have to use C. So it has a couple of macros. Those are, just to help us filling out those bytes. Where is it coming from? On my system, and I think on every system, this is coming from libc directly. Yes, So this is I'm pretty sure this is there on every Linux version. Okay, let's go back to it. So this is our only dependency. So we started with a couple of includes. I don't think we need actually all of them, but I just added them. So we will create our header. So this struct is coming from the elf.h. And we will create it here directly in the initializer. So the first line is the 16 bytes long array, which has the magic elf bytes. And those we can fill out from these macros. Let's take a look at it. So this is the man page. And yes, so if you are doing this, I can't show both pages at the same time while I'm writing the code, but this is how you can do it. You just leave this open and then you write the code, and or either this page or the header file directly, and just go from line by line. That's all I do, but I will not move back and forth unless there is a big reason for that. So we have these handy macros defined for us, and we just have to fill it out. So the 1, 2, 3 is the elf. But there are other fields in this array. The next one was that we are on a 64-bit system, which is hidden behind this macro. So this one, the fifth byte identifies the architecture, and we use this one, elf class 64. Maybe I will move back and forth. So next one is data, and we are in a two's complement little endian system. So that is elf data to LSB. This one is current. And this one, the ABI will be system V. As I mentioned, system V is the default ABI on many systems. And we don't need anything special. I don't exactly know the difference between this one and this one, so what Linux adds to this. Elf is extendable, so there could be some extension. That's my guess, but I did not look it up, and we don't need this right now. The next one will be the version, which is, I think it has to be 0. Yes, and then we need a couple of zeros after this, and then we finish with the first array. We could close it here, but I will put all the zeros here. So this was the first line in the struct. The next one is the type, and we want an executable. And this machine has a 64-bit CPU and x86, not ARM. I have no access to an ARM yet. Now the entry point, we will just grab one from. So let's take a look at the main again. So this is 400,000. We will grab this one. This will be just a dummy value at this moment, but later we have to make sure that this is where our first instruction will be mapped in the virtual memory. I'm pretty sure this can be everything, so this can be 0. I think there are some areas in the virtual memory that is forbidden, so you should not put it into the stack at the top, or VDSO or some other fields. I don't know exactly where it is, so we will just pick one because this looks this is a static executable, and surely that is a safe address for this. So we will choose this one now. Yeah, this is the address in the file of the program header. We will have one, but not yet. But later we will have one. We won't have a section header. Maybe we will write 0 here for now, because we don't have yet a program header. At the first stage, we will just create a header file and a header struct and see what readelf says about it. So this is the number of program headers is 0 and the number of section headers are 0. So this binary is really just a single header. Let's quickly look at this last one. So the machine, these are the definition. Yes, so we don't have a section header, so this will be, we have to put this one here, which might be, I don't know, 0 or something like that. Yeah, so all we have to do, we have the header. Let's write this to a file, to a binary file, and yeah, that's it, and see what happens. I will use standard C, not Linux, not open, not the Linux syscalls like open. I will use C API here. Let's call our binary bin. Because why not? Yeah, I did not close this one. So we just write out the header to the bin. Let's compile it. So we have the 64-byte bin here. Let's immediately read it up with readelf. Okay, it recognizes it. So tools complement little endian elf64 current system v ABI version. Okay, executable. The entry point is there, and we don't have any program headers or section headers. So I think this is already pretty good. So what we need next is the program header. What does a program header do? The program header loads up a section of the file, and we will have a single section of the file. We need actually the object code, but the processor understands. So the instructions in object code. And also we want to create a hello word. So we will need the string hello in it. That's data. That's not an integer that we can just add as an immediate value into an instruction. We have to store it somewhere. So we have to store the hello string, and we need also the instructions. And for this, we will still, again, we of course we could open the Intel manuals and put it together, but it's better to go from the other direction first. So here I have this hello ASM file. Let's take a look at it. I used this file in different videos before, but just for this video to be self-contained, I will go quickly over this. So this will use the NASM, which is the NetWide assembler format, but there is nothing specific there, not a lot of specific things. So global start, the linker that we will use to assemble this binary requires by default a start symbol label in it. So this is what it will look up, the linker, and the first instruction here will be put into the to the entry point of that binary. So that's the global underscore start, and this is where that starts. Section text is where we have runnable code, actual instructions. Section data is a different section where we can put like the hello string here. We edit and we add the name to it, and we can refer to this address where this data is in the memory by the name of message. DB means data bytes, I think, and we have here we have a couple of characters, hello, and this 10 is the new line. So this is just a couple of bytes together, a hello string, exclamation mark, new line, and we will refer to that message here. Okay, let's go quickly over this. What we are doing here? We want to write out a message, and for this we will if you cut out everything, the narrowest thing that is needed for this is a system call, and we will call the write system call for this. And to exit a process normally, not with segfault or anything else, we have to call another system call exit. And for the simplest hello word, you absolutely need these two, but nothing else is needed. So really just a couple of instructions. The system a syscall, you can think of it as a function call. They are not exactly the same, but it's very safe to think about them as function calls. They require some arguments, and you put the arguments into these registers. So the RAX register is where you put the number of the system call. The system calls don't have names. You have to refer to them by number. And then the various parameters will go in this order to the various registers. So it starts with the write system call. We will the write system call's number is 1. We move it to the RAX register. Then we add, it requires a few parameters, 3 parameters. The first is the file descriptor, which will be the 1, which is the standard out, which we get from the parent process. We get a couple of file descriptors in open already. We don't have to do anything with that. We get this for free. So we will point it to the standard out, and we need the data, actually, a pointer to the data that we get via the message. So this is where NASM helps us, that it will compile it to an actual address in memory. And then we need to tell it how many bytes from this address, which is 7 bytes, because the hello exclamation mark and the new line is 7 bytes. And then we call syscall. At this moment, the kernel takes over, writes it to the standard out, and we got back after this some moment. We will get back the control at the next line, and then we will just simply exit. We will call the 60 exit syscall, which is the number of the exit system call, and the exit system calls needs a number, whether it was successful or not. 0 means it was successful, and the other, anything else which is not 0, will be the return value, which you can get on in Bash. You can see which number the process exited, and then we call syscall again, and we will not get back the control after this. So after this, the kernel will kill the process. Okay, so this will be our code, and let's compile it quickly, because we don't need the assembly. We need the object code. Okay, so it is a multi-step process. So we now got the object file, and now we have to call the linker to link it together. Okay, let's call it. Yes, it works. So how big it is? It's still quite big, even though this was assembly, but the linker added a couple of stuff to it. Okay, what is needed? So we need the object code for this. Let's take a look at no. Let's first look at the elf header of this. So it has an entry point address to this 400 and 1000. That's the and it is also an executable and a systemd API. So it is pretty close to what we want to write. Let's take a look at the program headers. It has 3 of them. So a readable, writable, and an executable. So in the file, at this offset, we should see the code, the object code we are looking for. And either here or here, we will have the hello string somewhere, which is basically this is the file offset 0, which is where the elf header is located. So we don't need that. So the hello string must be here somewhere, and it's 7 bytes. So we know exactly that this is where the hello string will be, and it's just not 25. This is it's 47, I think, 47 bytes. Okay, let's take a look at the actual bytes in the file. So this is file offset 2000, and this is our hello string. So this was the readable, writable page. When the program loader loads it up, this part of the file, these 7 bytes, will be mapped to a readable, writable memory page. And I forgot I think we did not look up the virtual address of it. Anyway, this is our object code. 47 bytes, if I remember correctly. And these are what we need. Now I will not go into it. That will take a lot of time, and we don't learn a lot from it to interpret these ones. But you can look up the Intel manual, and you can look at them in both ways. So you can look at this one of B8, what it is referring to, and you will see that this will be actually not the RAX register. This will be the 32-bit variant of the RAX register. So the RAX register is 64-bit, and you can either move 1 as a 64-bit value to the RAX register, and there is an instruction and object code for that. But NASM compiled this. It recognized that we don't need that. There is a much shorter variation of it, and I always forget what's the 32-bit variant of the RAX register. Sorry about that, I always forget. So what this instruction does, it moves, this is just 32-bit, not 64-bit. It moves 1 to the lower half of the RAX register, which was on the 32-bit CPUs, and then these CPUs will automatically zero out the upper half. So why NASM does this? Because this is a lot shorter code. It's just 5 bytes instead of at least 9 bytes. Because 8 of them will be the 1, which is a 64-bit. Has to be a 64-bit long immediate value, and I don't know how long the instruction is, how it is encoded. So you can look up at this B8 in both directions, either by looking up B8 and yes, this is a move instruction, or look at the move instructions and look at the object code. Okay, this is another move instruction, but to a different section. So this will be the write system score number. This will be the std out, and then we need the message, the address to this pointer. So this must be the virtual address of this part in the memory. This one probably is the move instruction, and the rest should be up into this should be the address 1 2 3 4 5 6 7 8, or these two actually, the move instruction. Let's take a look at readelf again. So the hello is mapped to this address for 402,000. So that let's go back here. Yes, so this is actually this is the instruction. So this third, yeah, I know why. Okay, so this must be so these two were 32-bit variants of the 64-bit move instructions. So this was compiled to, because this is short as well. These two are short, the object code as well, and these doesn't that probably did not have space anymore for that. And we got the address here. So this is 402,000. Okay. And the next one, we have to send the seven bytes. So this must be the move instruction for that register, which I forgot now. But we see the 7 number, and this one I recognize. This is these two together is the object code for the syscall, and we will see this will be the second part, second syscall. So at this moment, this was the write syscall. We put hello out the std out, and now we can see B8 again. So we will set up the next system call, which is, this is 60, and also 32-bit. So that's where it ends. And the last one is the XOR instruction, which just zero out. Apparently this needs 3 bytes, so we zero out that register, which I never remember them. I'm sorry, but it's in the code. It's what it does. And then syscall again, and the rest is this star means that the rest is 0. Everything is 0. Okay, so what is the plan? We need this code. This will be the meat of the binary we write. So we will grab these bytes. We will have a single section which will be readable and executable. And we will put the hello string there, and also the instructions. What could go wrong, right? We could also make them executable to make it even less secure. Anyway, so we will put this string there. Then we will move everything like up to this into the binary, but we have to be careful that we have to rewrite this address based on that processor's virtual memory to point to this one. And we have to make sure that the entry point in the elf header points to this byte. This is the only non-trivial part. Everything else is just basically copy-paste. So this is our current plan. Let's move back to the code. So we have to we have to write now a program header, and also we have to create these bytes. But at least we know the size. We know the size of everything, and that helps a bit. Okay, here is the program headers struct, which is a 64-bit program header, and it is 56 byte long, and we can just go over it and fill out. So we will need a load type, and we have to set up the file offset correctly, and the virtual address which we will make up. But we will be around this number because we saw that this is a safe number, and I did not look up the exact spaces where we should put our entry points and the code. Why 78? Because we will put the program header right after the elf header. The elf header is 64 byte long. The program header is 56 byte long, which is 120. So this is the file offset where the 78 where our binary will start. I mean the object code and first the hello string and then the object code. And the virtual address and the file must be aligned. They must be on the same alignment. So that gives us this number. This will not be our entry point. We have to rewrite the entry point address. This will be actually 7 bytes later. So let's do that now. So 8 plus 8 is F. So that's where our first instruction should start, because 78 will be in the virtual address will be the hello string, the first byte of the hello string. These are the that we need an executable page. So this load section, how it maps to the memory, which should be executable, because this is where we will have our code, and it should be of course readable as well. And if you would want some self-modifying code, we could put writable as well here, but we don't need that. How where it is aligned in the file, that's where it should be aligned in the virtual address, and we have to add this here as well. And now we need our bytecode or object code. We are not writing Java. So we will start with the hello string. Let's write it the same way how it is in the hex dump. So this was this line, but we continue it. So this was in the assembly. This was mapped to its own memory page as a read-writable page. But now we put it together with the executable code, and now we start with the B8 and the others with the instructions. So this was, but actually not the RAX register, but the 32-bit variant of it. And what we send there, a 32-bit value. This is an immediate value. This is the second parameter, which will be again 1, because this time this is the std out, the file descriptor 1, and we are in little endian. That's why we have to write it backwards. And now we have to know the right address. So what address we need? We need this bytes address, the hello string's first bytes address in the virtual memory. Where do we map it? This section, this to this place. So we need this number actually here. Yes, we need the number of bytes now. Then we need the system call, the syscall instruction, which was F. Okay, now we need the exit system call, which will start with B8 again. And we send 3C there, which is the 60. And this is the ancient old technique to zero out a register. So this will be the return value of the binary. Okay, we have everything. Now just let's write these things to the file as well. Okay, so we just write everything in the right order. First the header, then the program header, then the object code. Let's hope I did not make any mistakes. At least it compiles. So we wrote our bin. Oh, I think we missed something. Let's go back. I just remember that we yes, in the header we have to write actually where is the offset of the program header. Yeah, let's not forget these parts. Okay, the entry point looks good. So this points to the first instruction, not to the hello string. Yes, and we actually have one program header. I think I missed a field here, but it's not really needed. It can be 0. And we don't have any so this is the section headers size, but this can be 0 as well because we are not using it. Okay, let's compile it again, run it again. No, we are looking at the wrong one. So this is what we wrote. Here is the entry point. This is where the section program headers start. We have one program header. Size of the program headers. Okay. Let's take a look at the program headers. So we map the 78 byte of the this is the offset in the file to this virtual address. It has readable and executable aligned on this byte. Let's take a look at it with hex dump. So the first 64 bytes are, this is the elf header. So this is the elf header. It starts with elf and there are a couple of things there. Then we have 56 bytes, which should be this long. This is the program header. No, one more line. So this is the program header. And right after this, it should start at 78 byte, which is correct. This is our hello string. We can see it here. This is our hello string, and then we start with B8. B8, 1, BF. Yes, the only non-trivial part is the, yes, this was the only non-trivial part, that we needed the right address that points back to here. And we see this 2 system calls. I think it's safe to test it. Chmod. Let's run it. It worked. So just let's take a look at this. We have a, why is this so big? Because we created a static binary. Anyway, so the normal main one was, which turned out to be a shared library, was around 20K. The normal C hello world. The ASM version was 8.7K, but this is full of zeros. And our binary is 164 bytes, and you can see it works. How can I get back the... Yes, so this is the return value of the previous binary, which is 0. That's what we wrote there. Amazing. I want to show one last thing, because this is the moment when you can start. You have something working, so you can start playing with it. And I want to encourage you to start playing with it. Let's add something here. Just as a joke. How many characters? 1, 2, 3, 4, 5, 6. So we have to change a few things. So what I am doing, I am putting something into this binary in a place where it does not make any any problems. But so basically we are hiding something in the binary, and in a very dumb way, of course, but still it's I think it's funny. And if you start playing with these things, I think it helps you to take better control over these things. So we put these 6 bytes next to the, maybe next to the program header. This means that our object code will shift a bit. Maybe we should add it to the end of it. Then it's not shifting, so I don't have to change things. Yes, let's move it below. Yeah, that's feels better. Because now we have to rewrite the offsets and the alignments. I don't want to do that now. So as you can see, right after the last system call, I put this hidden thing here. Let's see whether this does anything. No, it still works. And well, you have to trust me on this. As we are controlling all the offsets, and the only important thing is that the binary must start with the elf header. After that, we can put things there, because there is a section in the header where is the first program header, where it starts. So we can put a picture there if we want, and then we we will just set up that the program header starts after the picture, and we have to adjust if we use any. The only thing that can be ruined is basically the alignment, because the rest of the code is self-contained because it works in the virtual memory, but we can fuck up the alignment. That's why I moved it to the end of the file, but believe me, you can put it into the middle. So you can. So this is the elf header. You can easily put something here and move everything a bit further away. So let's recap. We created this short binary, which was 164 bytes long. It is a working hello world. We can see that it writes out hello by creating a single header, single program header, and putting both the code and the data together into a single memory page, readable, executable memory page. Yeah, I will stop here. It was already much longer than I expected, but I think it was important to this branching off to various parts, because like looking at why it is a dynamic library and things like that, because I think that's how we can understand it. We have to put the bushes away to see really what's underneath it, and this short binary is understandable. The main, like what we got with from C by default when we compile it. So this code with a couple of program headers and section headers are not understandable. Oh, I want to mention something. So that this code is you can put this into GDB or look at it with object-down, because those are relying on section headers. I don't want to get into this now, but as you can see, for the kernel itself to load it and successfully run this binary, it needed only the program headers. Okay, thank you for listening. Bye bye.